think the way I'd like to talk to you is...
So I'm going to have Frank do the seminar.
Oh.
So this is
Frank Platt. This is not a seminar. It's a primer.
It's a primer, that's right. It's not a seminar, it's a primer. So, so he's going to do some brain transfers without the goop. And the topic is operational subjective statistical methods. It's a primer on subjective probability and statistics in the mode of Bruno de Finetti.
Sure. Yeah. Good. So I'm happy to talk to you. And the way I thought I would talk to you is sometimes at a party you'll meet someone and they'll say, "Oh, what do you do?" I say, "Well, I'm a retired academic." But I taught you math and stats. They asked what are you interested in? I'm interested in probabilities. My main line of work, it had been the main work of my life, and still it excites me quite a bit. I'm very interested in the ideas, both the history of the ideas and the development of ideas, particularly from the subjective point of view. So, and they say, "Well, what's that about?" I say, would you really like to know, or would you like to just have an idea? And they might say, "Well, because if you would like to know, I need to talk to you for about 10 minutes or 20 minutes. We could go longer if you like, but it's not going to. I can't tell you 2 seconds, 5 seconds. Would you like to?" And sometimes they will say, "Oh, I don't think I'd understand," but that's fine. I said we can talk about other things. That's good. But if you would like to know, well, let's try. I'll talk and you'll get an idea. And so that's the way I'm going to talk to you, because I think you all would like to know, because you came and you have surely enough background to understand everything about it, because all that you need to know about is arithmetic to make it go arithmetic and linear algebra. So probability is in the state of a huge argument, a deep argument. There's been the deep argument has gone on since Europeans surely started thinking about it in the 16th century. And this is the bit, but I'm not going to get into history or philosophy or what things mean so much. I'm just going to spend my time constructing for you the subjective point of view. But I should tell you that the basis of the argument, what the argument is about, is what do you mean when you say probability my bicycle will have a flat tire this month is 0.13. Not whether it's 0.13 or 0.14, but what do you mean when you say something like that? And by and large, there's in the main, there are 2 main views, quite distinctly different views, and many variations on the themes, as you can imagine. One is called the objective view, and one is called the subjective view. The objective view has dominated the 20th century, and still most probabilists and statisticians think in these terms as well. The objective view is that chance, randomness is part of nature. Things happen by chance. There's a probability that we will record a frost at the weather station in Christchurch at the airport tonight. There's a probability my bicycle will have a flat tire this month. There's a probability that you will die before you're 57 years old. There's a probability that there are probabilities things happen by chance. And the one thing is that we can't observe these probabilities. We will observe my bicycle does or doesn't have a flat tire this month. You will or you won't die before 57. But we won't observe 0.13 or 0.14. Probabilities are in principle unobservable. Yet, they are at the heart of nature. Things happen by chance. I don't want to get into where the views came from. I wrote a book called Operational Subjective Statistical Methods, a mathematical, philosophical, and historical introduction, which is available in the library, published by John Wiley in New York, 1996. If you'd like to read the book, there you can read the book. But so you can't observe these probabilities, but all we can do is estimate probabilities. So what we're going to do, if we want to estimate the probability that my bicycle will have a flat tire this month, is we'll go find a bunch of other bicycles that are just like my bicycle, and then we'll find out how many of them had a flat tire last month, or we'll find out how many of them had flat tires during the month of May in Christchurch, New Zealand last year. And we'll count up of the 117 bicycles we find like this, that last May, 11 of them had flat tires during the month of May. We'll estimate the probability that my bicycle had a flat tire this month is 11. Well, and that's what statistics is about. Statistics is a way of estimating the probabilistic generating structures of nature. We make hypotheses about whether the structure is like this or is it like that. Is mu bigger than 0 or is mu less than 0? x1 through xn or IID, normal mu sigma squared. Null hypothesis that mu is bigger than 0 and the alternative is less than 0. And we create statistical procedures with properties to answer tentatively these types of questions, or to estimate the value of mu, or things like that. The subjective view is this probability that my bike will have a flat tire. You can't observe it, you can't see it, taste it, touch it, feel it, hear it, then it's not there. There isn't any probability. Probability doesn't exist. Science has nothing to do with things we can't feel or we can't touch. Science has to do with the empirical world that we meet and what we think about it, what we think it will be like when we meet it next time. Well, so there isn't any probability that my bicycle has a flat tire this month. The objectivist thinks there is a probability, and it's a property of my bike. It's a property of how old it is, the make it is, when I changed my tires last, where I ride, when I ride. But for the subjectivist, there is no probability, but I don't know that I'll have a flat tire this month. Neither do you. Neither do you. Neither does James or Benedict. None of us know. None of us are sure. Probability is not a property of my bike. Probability is the representation of an individual's uncertainty about this observable question. Will my bike have a flat tire or not? Just because we're not sure doesn't mean we know nothing. In fact, we're sure of virtually nothing. Benedict has a black shirt on, and James has a black sweater, and Rosa has a yellow shirt. We're certain of that. There are 4 people in that row, Bill's sitting over there, and we're certain of all this, but is my wife alive? She was when I left her, just an hour ago, but I'm not certain. And any subject matter that we study, even the people who know the most about it are uncertain, if you really ask them. Now sometimes, the people who know the most about it might be uncertain to the extent of maybe something will happen plus or minus 2 minutes, whereas someone else might know that it will happen plus or minus 2 days, or plus or minus 2 weeks, or 2 centuries. But everyone's uncertain about everything. There is a logic of certainty, the logic of 1 and 0, true and false. If A is true and A implies B is true, then B is true. If I said A is true and A implies B is true and B is false, you would say, stop, you've contradicted yourself. I don't know what you're talking about. It doesn't make any sense what you're saying. So there is a logic of certainty. We know about the logic of 1 and 0. The only thing is that we're certain of virtually nothing. We have three people in that row, 4 in this row. I've got a red thing on, Bill's got a blue shirt. We're certain of this, but everything that's important to us about every subject matter that matters, no one's certain about. The logic of certainty is completely irrelevant to science, commerce, architecture, civil engineering, law. It's completely irrelevant. We're uncertain about everything. Probability is the logic of uncertainty. Just as in the logic of certainty, there's a distinction between, we say, propositions and assertions. The door is green. That is a proposition. It could be true or it could be false, but the door is green. It's the same words, but if I say like the door is green, I'm asserting, I'm telling you the door is green. That's something different. And in the development of arithmetic through Frege, made a special symbol. I assert A. So, well, if you want to assert A, there was a little turnstile. Well, if you don't know whether A is true or false, we write P of A. P of A, probability is an assertion. There's nothing to be estimated. There are no probabilities to estimate, and so the best unbiased, linear, consistent, efficient estimator of the probability is a misleading falsehood. And so is all its Bayesian appendages. The Bayesian estimate of probability is a falsehood too, because there isn't any probability. But there is a subjective theory of probability. It comes from Bruno de Finetti, and that's the way I'll explain it to you. And it goes like this. Life is going along. There are no repetitions. We were once exploding gases, now we've turned into this, we're going to turn into something else. There are no repetitions, there are no same conditions. Every condition is different everywhere, every time. But something's happening, and in the course of time, as part of our experience, because we would like to communicate with each other about the things that we're experiencing, we make measurements. So we make measuring devices, and we call the result of an operationally defined measurement, where you do this, you stand on this scale, and this scale, so now we're quite familiar with this. See, our parents used to stand on scales, and the needle used to swing around, and they'd say, oh, there's some true weight for me, and there's a continuous possibility of readings, but we can only measure them with error. But now we don't stand on scales like that anymore. Our scales are digital. So the one I stood on the other day was, it could measure 0, something, something, point something. So the only possible readings that this scale could make would be 0, 0.0 up to 99.9. Those are the only possibilities there are. And the operational measurements, I'm going to stand on the scale, look down and see what's the number, and I'm going to call that quantity x. So x is a quantity. Every measurement, it's Roman, it's not Greek. There's no Greek things here. We live in a Roman world. The Greeks, that was metaphysics, what the muse and the sigmas are about, and that's explicitly why the objectivists write in those terms. So we live in the world of x, and x is a quantity. Every quantity is like this. Every quantity that we can measure has the biggest thing it can measure, the smallest measurement it can make, and a finite, discrete number of possibilities in between. That's what we call the realm of x. Well, we don't know what x is. And it doesn't matter what kind of a thing x is as a measurement. It could be a measurement that was made a couple of days ago. For example, x is the quantity that the scale read when I stood on it the other day. I'll tell you, I had tennis shoes on, and I was wearing some clothes. I wasn't naked. And it came up with some number. What's that number? Call that x. The realm of x is the set of all possible numbers that it could be. So in that case, the realm of x, x1, x2, xk, so up there are the numbers 0, 0.0 up to 99.9. That's the realm of x. Now, we don't know what x is. Neither you know nor I know, but we're all uncertain. Your uncertainty about that question is different from my uncertainty. Mine just has to do with my memory of what number did I see. Yours has to do with, yeah, how big is this guy? What was that scale like? Was he wearing? Each of our probability is not a property of me or the scale or the measurement. The probability is, your uncertainty, the probability is a property of the measure of your uncertainty about it. We talk generally about quantities. Some quantities can be, their realm is just 0 or 1. Do I have a flat tire or not when I go out to my bike? 1 for yes, 0 for no. Quantity is either 1 or 0, the realm is 0 or 1. In that case, we call the quantity an event. An event is no way different from any other quantity. So we're just going to work like this with quantities. Now, I'm uncertain as to what the quantity will be, so in expressing my uncertain knowledge about that quantity, I assert my prevision for x. It's called P of x. P of x, or P of E, or P of P. Prevision, if an event is, if x is an event, its realm is just 0 or 1, then your prevision for the event is the same as your probability for an event. Prevision for anything. So what's your prevision for the weight that is set on the scale when I stood on it the other day? And the way you think about that is you say, well, would I rather have 20 cents or would I rather have the number that is set on the scale, cents? Which would you rather have? Which measures in kilograms. Would you rather have 20 cents or the number that's never either one? You'd say I like the number on the scale. How about 100 cents? Would you rather have 100 cents or the number of kilograms that I sense? I'd say I'd rather have 100 cents. How about 30 cents? Oh, I'd take the weight. How about 90 cents? I'd take the 90. How about 40 cents? I'd take the weight. 80 cents? Oh, 80 cents? 80 cents? Am I more than 80 kgs? About 85 cents? Let's go back to 90 cents. 40, 50, I'd have the weight. 60, 70, I'd have the weight. 90. If you could come down to the point where you came to, they said, 73, 74, maybe 77 cents. It comes 77 cents. I'll go up to 77, taking the weight. I'll come down to 77, taking the money. And 77 is the number where I don't care whether they give me the money or the ticket. That's your prevision. Okay? That's how we define a prevision operation. And I say scale down because we're talking about cents. If we were talking about units of millions of dollars, well, we'd all take 1 million right away rather than before we're even looking at the weight. I'll take a million and run. That has to do with utility theory. But so in utility theory, well, we get down to small scale. So to deal with your uncertainty about things that have a big matter, like are we going to have a nuclear reaction accident and a leak in the Mississippi River this month? Well, now we're talking about things that have big, or not. Which would you rather have? So we're talking about small scale. There are ways to deal with those, but I don't want to get into it. This is a primer. This is the way it works. Okay, so now you can say whatever number you want as your buying and selling price. And you can't be wrong, because you're not saying anything about my weight. You're saying about what you think about my weight. Your provision is whatever. Your provision could be 73, yours could be 77, and his could be 82. You're all right, because you're just you're telling us. You're telling yourself. No. You can say whatever number you want. The only thing is, suppose you had said 120 is my provision. So $1.20, I'll give $1.20 as opposed to getting the number of cents that's on the scale. Well, we know the scale can only go up to 99.9. So if you said 120, I'd say, okay, I'll sell you the ticket. Here's the ticket. It says the bearer gets the number that sits on the scale. You give me the $1.20, I'll give you this ticket. Now all the number can be is 0, 0.01, 0.1, 99.9. No matter what, of all the possibilities, you lose. You're a sure loser. That's incoherent. See? So one thing you can see for sure from the very beginning is that your provision has to be between for a quantity, it has to be between the smallest possible value and the biggest possible value. Now suppose you think about a vector of quantities. There's my weight, there's Bill's weight, there's my weight yesterday, there's my weight today, there's my weight tomorrow, there's all sorts of quantities. And in fact, because there's so many quantities that we're interested in, oftentimes we don't spend our time getting down to our prevision, down to the very last digit of what's right. We might end up with intervals, because I can't think anymore about this, I got to think about lots of other things. We can live with intervals too. Okay, so now we have a vector of quantities, x1 through xn. We have a provision for each one of them, like the milk yields from n cows in a dairy herd. How much is this one going to give this year? We're going to add it up every year, every day, once or twice or 3 times milking. There are all sorts of ways to milk cows. X1 through xn are the annual weights. Usually they're milked for 305 days. And they're given 60 days off, the last 60 days of their pregnancy, and then they're starting to be milked again. So here we have weights for so many cows. So what's your provision for the weights yielded by each of these cows? Well, there's a vector of quantities. Your P for a vector is the vector of your provisions. Your provisions for the vector are coherent. Where are we here? Provisions for a vector is coherent. Why doesn't it go forward?
Just use the up and down arrow. So it's down if you're looking at the machine. Okay.
I got it.
I'll hit the space bar to go down.
Yeah. Okay. So the vector of quantities. Okay, so one thing is that so the vector of quantities is x. Now each of these quantities, because of the measuring devices for measuring milk, again, there's finite and discrete possibilities. So for this vector of measurements, there's a list of vectors. All the possible, they could all be 0. They could be 1, 0, a vector of a set of vectors of the same length, finite and discrete. That's the realm for that. Your provision for the vector is coherent just so long as, well, okay, your provision let's look at this. Your provision for vector is coherent as long as there's no vector Sn for which, see, various xn's, those are the members of the realm. Those are all the possible things that this vector might be. And your P of xn is a vector of numbers for which you said you you don't care whether you get x or whether you get capital Xn or whether you get p of xn. Now, in fact, you're going to get this for some n back. Now, there's no vector Sn for which, what the idea here is that, suppose these are just numbers for now. See, if S is a positive number, that means you're going to lose p of x, the price you gave, and you're going to get x. So if S is positive, that means you're going to buy x for p of x. But if S is a negative number, that means you're going to get plus p of x, and you're going to lose x. So when we say there isn't any Sn, positive or negative, when we're talking about a vector of quantities, it's saying when you specify your provisions for a bunch of things, that means nobody can look at this whole vector of provisions you gave and said, whoa, you said you'd buy or sell this one for that much, you'd buy or sell this one for that much, you'd buy or sell this one for that much. Let's take an example of rain and no rain. Is it going to rain tonight or not? Suppose you said my P for rain is 0.2 and my P for no rain is 0.85. What would you say? You'd say I'll buy or sell rain for 0.2, I'll buy or sell no rain for 0.85. You'd say I'll sell you both of those. Here's a ticket, you give me 20 cents for no rain. Here's a ticket that says I'll give you $1 for rain, you give me 85 cents for that. You gave me $1.05. I gave you 2 tickets. One of them's worth $1 and the other one's 0, or the other one's worth 0 and the other one's 1. But no matter what it is, you lose. You're a sure loser. That's incoherent. So, you say, your provision for vector is coherent as long as there's no vector Sn for which Sn transpose Xn minus p of x is negative for no reason. Because, what does that say? That's like, if you think about linear algebra, S's are the coefficients of a hyperplane. Sn transpose x, that's something times x1 plus n minus x plus n less than. There's no hyperplane S that will separate x from p of x for every possible x. The idea is that these possibility vectors are sitting out in space, and their convex hull is the set of all the supporting hyperplanes that bounds in your p of x better be in there. Because if it's outside of there, then we can find a separating hyperplane that will separate your p of x from all the x's, and you lose for sure. That's how coherency does. Coherency requires that p of x must lie within the convex hull R of x, since there's no hyperplane can separate them. And also, coherency also implies that p is a linear operator. Your p for any linear combination of x's must be the same linear combination of the p's. That's what happened in the rain and no rain. We found out that p for rain plus no rain has to add up to 1. Because they're either 0, 1 or 1, 0. Those are the only possibilities there are. So their sum is 1, so your p's better sum up to 1. That's just a property of coherency. It's not an axiom of Okay. Now, the fundamental theorem of prevision. Isn't this funny? What's the fundamental theorem of calculus? You know the fundamental theorem of calculus. Integrals are recursive differentials. They're the inverse of each other. Fundamental theorem of linear algebra. There is one, not very well known by that name, but there's a very funny one and a very nice one. But fundamental theorem of prevision, fundamental theorem of probability, this is it. It's in De Finetti's book, chapter 3, section 10. And anybody who looks in De Finetti's book, their fundamental theorem of probability, they look and they see this, because they're thinking they're going to find a strong law of large numbers or something like that. And they see the theorem that says, whatever you assert about any n quantities whatsoever, there are computable, necessary, and sufficient bounds in your provision for any further quantity you want if it's coherent with p of xn. That's the fundamental theorem. Now, why is that true? Because the vector xn plus 1, so one thing I should say about this vector, x1 through xn plus 1, it's equal to the realm matrix. Let's take this realm, all the vectors that are possible, and let's multiply it by the constituents of a partition. Is xn, is the vector the first possibility? Yes or no? Is it the second possibility? Yes or no? Is it third? Is it the kth possibility? Yes or no? This vector, we don't know what it is, but it better be, it's got to be, this matrix times, because it's, one of these things is yes, 1, all the rest are 0, so this thing's going to, that 1, whichever one it is, that is the one, is going to pick it out.
Sorry, Frank, what does NASC stand for again?
Necessary and sufficient conditions.
Oh, yes, of course.
So it's going to pick it out. So you see so your P for x1 through xn plus 1 has got to lie inside the convex hull of these things. But when you've specified your P1 through Pxn, you've specified n linear conditions on this Q vector, the constituents of the partition, your P's for all these probability, for P's for all these events. Remember, one of them is 1 and all the rest are 0. They add up to 1. They partition 1. Partition in the sense of an arithmetic partition, not a set theoretic partition. If you study Kolmogorov, you know about set of all the subsets and partitioning a set and all that bullshit. Well, partition of a number is partition of 6 are all the integers that add up to 6. There's 1, 1, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1, 1, 3, 4, they're all the ways to partition. Well, this constituent vector, they're all numbers, they're all 0 or 1, and they add up to 1. So they partition 1. It's partition in that sense. So we get n linear combination, linear restrictions on this thing, and the last one is the last row of that realm matrix times this thing, and it's a linear programming problem, isn't it? Maximize and minimize this last linear combination of these things subject to the constriction that the first n of them are equal to those things. That's the fundamental thing. This theorem includes all probability inequalities of special cases, including Tsarychev and Kolmogorov. You can read an article in mine about that if you like. Okay, now what about conditional prevision? Conditional prevision, if you studied economics and think about options and what do they call those things? It works like this. What do you mean by saying P of x given E? P of x given E is also a number. It's called your conditional prevision. And it says you're specifying your indifference between P of x E, that's a number, and what does this one say? It says dollar sign. We'll put a dollars in that dollar sign. Xe, you see if E is 1, you're going to get x. If E is 1, this part is 0. But if E is 0, E is an event. If E is 0, this part is 0, and this means you get your money back. So you think about your price for a conditional transaction. P of x given E. P for my bike having, let x be the number of days before my bike gets a flat tire. Number of days, there we go, let x be the number of days before, okay. So let E be the event that it gets a flat tire this month. Now x could be any number. E can be 1 or 0. Conditional on being this month, how many days do I think it will be? Because if it's not happening this month, you're going to get your money back. So you just think conditional provision, it's your price for a contingent transaction. So that's what conditional provision is. It's another assertion. Once you assert P of x given E, suppose you would define a conditional quantity. See, in Kolmogorov, there's no conditional quantities. What are you talking about? Conditional probability is defined to be P of E1 given E2 is P of E1 and E2 divided by P of E2. That defines conditional probability. Here we've defined, operationally defined what a conditional provision is. Once we define a conditional quantity, and this quantity is xe plus 1 minus E P of x given E. So if E is 0, x given E is P of x given E. And if E is 1, x given E is x. Well, linearity of coherent prevision will tell you this right away, just from pushing through there. It's a coherency condition that P of xe equals P of x given E times P of E. There's no conditions that the probability of E has to be bigger than 0 either. How about let's do a drug testing. Here's a classic thing of drug testing. The objective is to think what we're going to do is we're going to get a class of all the people who are in the same age group, the same history, and all have the same illness, and we're going to give them this drug, and we're going to find out does something good happen to them or doesn't it happen? Sometimes good things happen, sometimes bad things happen. Something good happens or doesn't it? And we say, well, we've got all these people into the same group, so their success on these drug tests are independent of each other because you're all in the same group. You're having success with the drug has no causal effect on whether you're going to have the drug. So these are independent trials, And we'll find out how many of them were successes and how many weren't, and we're going to make an estimate of the probability that this drug has such and such an effect based on our trials. Well, subjectively speaking, there is no cause and effect. Cause and effect is an indefinable relation. And it's an old idea, very strongly, people have been very clear on it since David Hume. If you have studied any philosophy, David Hume, you would know. So there's, cause and effect means nothing. You can observe A and B, A and not B, not A and B, and not A and not B. That's all there is. You can't observe A causing B. Well, there's how about probabilistic cause? There's nothing to that, but no. See, for subjectivists, there isn't any probabilities either. So there aren't any probabilities either. But how about these patients having drugs? Given the drugs, they're all in the same group, they're all in the same weight category, blah, 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 blah. I surely don't regard them independently. If I were to regard them independently, that would mean here's E1, E2, E3, E4. Oh, you're all in the same group. My P that you're going to have a positive reaction is the same for all of you. Because you're all in the same group, you're all given the same drug, well, that's the best we can do, and that's what I think about you. I regard you all the same. Now, what's my P for you having a success on the drug, given that you had success on the drug? See, if I regarded them independently, it would say that it doesn't matter whether you had it or didn't have it. You're independent of each other because you have no cause. Your events are. I don't regard them independently because if I learned that, oh, the first guy I gave it to, he had a good reaction, I learned something from that. That makes me think more like you're going to have it. And when I see 2 out of 2, my P for you given E1 and E2 is different from my P for you given not E1 and not E2. If I regard them independently, those would be the same. I don't regard them independently. What generates all of the positive benefits of experiment, because that's why we do testing, by the way. Because we want to learn about the last one from the ones we did so far. That's why we check these ones, and that's why we do experiments. We don't regard them independently. Independence is irrelevant, completely irrelevant to all of sensible statistical testing and inference based on observational statistics. Completely irrelevant. Okay, now, where were we? Oh yeah, so what does characterize our, here's my opinion about you 4 people taking the drug. Maybe you all have, maybe none of you have a good result. Maybe one of you has a good result. If there's one of you, only 1 out of 4 has a good, my P is the same that it's you, and that it's you, and that it's you, and that it's you, because I regard you exchangeably. If there are 2 successes, my P is the same that they're U2, 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 or U2, or U2. If there are 3 of you, my P is the same that it's U3 and not her, U3 and not him, U3 and not him, U3 and not him. Permutation, it's called permutation invariance. Exchangeability means that you assert equal probabilities for any permutation of a string that has the same number of successes, irrespective of the order in which the successes occur. Sometimes about a property of the dairy cows that are at the 500 cow milk farm, the dairy farmer, all those cows, they were all generated from artificial insemination of sperm from exactly the same bull, and they're all purebred Holstein Friesians, and they all look exactly the same when you look at their picture. But the dairy farmer has to do his taxes and all that stuff, and has no idea one cow or the other. But his daughter does. His daughter knows all the cows. And so if you're talking about milk yields from the cows, whereas the dairy farmer regards them exchangeably, the daughter doesn't. That's a very important point. Okay? Now, regarding the events exchangeably, one of the things, it turns out that an equivalent, there are several equivalent ways to define exchangeability. Another one is that exchangeability, it's either one implies the other, that if you regard the sum and n as sufficient statistics, that if you regard n plus 1 events exchangeably, if your P for en plus 1 given Sn is equal to, given the sum of the first n of them is equal to A, is the same as your P for En plus 1 given the exact order in which they occur. That is, if the sum and the total number observed are sufficient for your inference about the next one, that also characterizes exchangeability. So, give a general extension to quote. No, that's right. No, I'm still at 35 minutes, isn't that right? Did I go to 5 too?
You're on 5 minutes 56 seconds right now, since the first start. So it's the second half hour that's running.
Stats.
So, I mean, I don't mind being here, Frank. If you guys want to go, you can go. Because we can have a double primer. They can watch it later, too.
Okay, now here's an interesting thing, is that if you regard... Oh, no, I guess I should say something about this. Here's a funny thing about... Let's go back up. I'll make you picture, you can imagine it. We're going to talk about two events. I'll show you something. I'll show you how to think about this next theorem. It's called the representation theorem for infinitely extendable exchangeable distributions. And it works like this. We're just going to have two events. Your mother is alive or not, your mother is alive or not. Okay? 1, 1, 1, 0, 0, 1, 0, 0. Those are the only four possibilities. And all right, so because if those, now let's think about those four events, 1, 1, 1, 0, 0, 1, 0, 0. Those four events constitute a partition because they add up to 1. One of them is 1, all the rest are 0. So the four probabilities have to add up to 1. So that means only 3 of them are free because all the probabilities have to be bigger than 0 because each one of those events is. So, okay, now, so the set of all the coherent probabilities for those four possibilities is equal to, in the Euclidean space, here's positive, 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 there's 1, 1, and 1. Okay, so there's the triangle, there's the equilateral triangle. All the vectors of any three of those probabilities have to add up to smaller than or equal to 1. So there's 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay, so that triangle, what do you call that thing? A pyramid. That pyramid in there, that corner, that's called a unit simplex in 3 dimensions. 4 numbers that have to add up to 1. The fourth one, these 3 that we're talking about add up to 0.2, then the fourth one has to be 0.8. They all. Okay, so the unit simplex in 3 dimensions is that. There's the equilateral triangle going down to the 0, 0, 0 point. Now, okay, so what we're going to do is put 0, 0, 1, 1, 0, 1, and 1, 0. Okay, those are our 4 possibilities. Now, all the vectors that sit inside there, each one represent all the probability distributions for these 4 events that there are. Now, exchangeability means that P of 1, 0 equals P of 0, 1, because that just changes the order in which they occur. So now let's look at these again. 0, 0, 1, 1, 1, 0, 1, 1, 0. Well, if P 0, 0, P 0, 1 equals P 1, 0 equals 1/2, that would be this point up here and 0 on these. Well, out of that pyramid, if we pulled out that triangle that goes through 0, 0, 1, 1, and 0, 1/2, 1/2, 0, that triangle pulled out of the space of all the possible probability distributions, that's the set of all the exchangeable distributions. And there's the set of all the exchangeable distributions. Up at the top is probability 1 for 0, 0, probability 1 for 1, 1, probability 0 for both of those, but 1/2 and 1/2 for 0, 1, and 1, 0. Let's see where they all are. Well, it turns out that, suppose we think about now a third event, and your mother is dead, or alive or dead. Well, whereas 0, 1/2, 1/2, 0 is an exchangeable distribution for 2 events. There's no way to make an exchangeable distribution for 3 events that will reduce to marginally 0, 1/2, 1/2, 0 for the 2 events. Regarding 2 events exchangeably by putting 0 on 0, 0, and 1, 1, and 1/2 on 1, 0, 1, 0, 0, 1, 1, 0, that cannot be extended to a distribution over 3 that's exchangeable. Now what happens to this triangle, I'll just wave you through. What's going to happen is that suppose we try to find out all the distributions that are exchangeable but over 2 but not extendable to 3. That's going to cut off the tip. How about those that are extendable to 3 but not to 4? Those are going to cut off little sections here. How about exchangeable to 4 but not to 5? Those are going to cut off some sections there. How about extendable to 5 but not to 6? And how about 7? And how about infinitely exchangeably extendable? And we'll come to theta times 1 minus theta. That's what this next theorem says, is that it says that if you regard the sequence as infinitely exchangeably extendable, which is never true for a finite population problem, a real finite population problem, but it's approximately true. This is a term. Then your P of Sn A can be written, probably that Sn is equal to A, can be written as, I forgot to put n choose A out front. Theta to the A1 minus theta to the n minus A. Doesn't that look like a binomial probability for independent events? Oh, it does. N choose A, theta to the A1 minus theta to the n minus A. But this says, and you have to mix it. This is a mixture distribution, mixed by some distribution function f of theta. So, now, a Bayesian would say, oh, there is some, there is a probability that your mother's dead. And it's theta, but we don't know what the probability is. That's what f of theta is. So I'll tell you what my probability is for the true probability, and that's how Bayesians talk. But remember, I might regard these things exchangeably, but your brother doesn't. Your brother doesn't. Huh? Because your brother knows something about your mother that we don't know. Anyhow, so there's no theta. Because somebody regards them exchangeably because my opinions can be represented this way, doesn't mean that everybody's can. And there isn't any theta, and don't go estimating it. So what you can use this theorem for is for, I miswrote this. This should say P en plus 1 given Sn is equal to A. Suppose I regard E1 through n plus 1 exchangeably. My opinion is about blah, blah, blah. That probability for En plus 1 given Sn is A. It says whatever that mixing distribution is, and there are ways to talk about it and ways to learn how to assess it, your probability for En plus 1 is theta mixed over by this your posterior mixing function on theta. This is a representation of the statistical inference.
So Frank, the buffer and the memory will last for another 16 minutes max.
That's okay, so we'll be done by then. Because the last thing to say is that if I do give the talk about scoring rules, and whether or not I do or don't, you'll want to know about this. So you mean some person's opinion is just as good as anybody else's? Well, this is good. Yours is yours. Your opinion is your opinion. You mean your opinion? I don't care. Science doesn't matter about what you think. It matters what's really true. All right. So that's how people talk. But the point is that we all are uncertain, and different people have different ways of they think differently, and so they have different ways of characterizing their opinions because their opinions are different. And the idea of a proper scoring rule is now Pn has to do with, suppose you have a quantity x that can be x1 through xn, and these are p at x is x1, x is x2, x is xn. We all have if you have a probability distribution, probability mass function Pn, and you observe that x is x0. It wasn't 1, it wasn't 2, it wasn't 3, it was 4, not 5, not 6, not 7. That when you learn, the score that you get, if you assert Pn, when you find out that x is 4, that x is x observed, that's called the scoring rule for Pn on observing that x is x0. The idea is this, if we have different forecasts by different people, they're all right, because they're not saying what's going to happen, they're saying what they think. Now, if you tell me what you think, you tell me what you think, you tell me what you think, and I want to buy some information from one of you, which one am I going to buy from? That's the idea. Well, let's see what you think about various things. Let's score your thoughts. That's what the scoring function is. S of a distribution based on the observation is a scoring rule for Pn observed x. The rule's proper if, now see, what this means is that if your prevision for the score that you get when you assert Pn, we say, what's your probabilities? My probabilities are Pn. Your prevision that for the score that you get when you assert this, once you observe x equals x0, because you don't know what x is, so you don't know that you're going to see x0. That's why you told us P1 through Pn. So you don't know what score you're going to get either, but your prevision for the score that you get is bigger than your prevision for the score you would get if you would tell us some other probability. where P, the prevision, is assessed with respect to your own P of n. The idea here is that if I know that I'm going to be scored, and these are my probabilities, oh, I know I'm going to get scored like that. So I think I can do better if I don't tell you my probabilities, I'll tell you somebody else, some other probabilities. Well, there are scoring rules that work like that. You know that you can do better by lying than by telling the truth. Well, a scoring rule is called said to be proper if your prevision for the score you're going to get is big. If you say your real probability distribution is bigger than your prevision for the score you're going to get if you say some other ones. That's what's called a proper scoring rule. And there are some famous log scoring. The log scoring rule is a very funny one. It's a very famous one based on a big mistake. That's what I'll tell you about next time. I find out some. It says that, oh, the score that you're going to get, it's called the log score. It's just the log of the probability for the thing that happened. Now, as you can imagine, what's your prevision for the score you're going to get? See, log P of I, those are just numbers. EIs are the variable. Your prevision is the sum of the PI log PIs. Oh, that's the entropy in your distribution. Ah, great. What the one talk I've just found this out is that entropy has a complementary dual, and it's called the extropy. It's very funny. Well, here are some other proper scoring rules. Quadratic scoring rule says, see, one of these E's is E1 through En. One of them is 1, and all the rest are 0. Whichever one is 1, we're going to take 1 minus the P that you gave that and squared it, plus all those that were 0, we're going to take 0 minus the P that you gave and square it. For all the not EIs. It wasn't 1, it wasn't 2, it wasn't 3, it was 4, it wasn't 5, it was... Okay, so that's the quadratic scoring rule looks like that. Okay, so that's... okay. I'm just going to...
So that's sort of a slight prelude to your seminar next week, right?
Yeah, and these are the last 2 slides. This is what the daily returns, percentage gain of the stock Dow Jones Index over the past 26 years. Looked like that. Some of you weren't born in October 1987. I don't think you were you? Was it? No, I don't think so. But you wouldn't even know. See, this is great variability we're going through right now. This is 2010. Well, in October 1987, the stock market lost 25% of its value in a single day. And it just came out of the blue. Look at that. Whoa. That was a big thing. But anyhow, suppose there are various ways to think about stock markets and blah, blah, blah. So there are 4 different distributions that we're studying. And I just wanted to give you a show that the way that we do statistics is there's no probabilities to estimate, there's no parameters, there's no estimating the jump points in the distribution. We're just saying, what's the stock price going to be tomorrow? You tell me what your probabilities are for that, and the next day, and the next day, and the next day, and we'll see how we do. Well, there are 4 distributions that are under contention. The log score, we add up the log score and keep adding it up each day. And it's a little bit different from that. But this one, oh, look, this is a quadratic score. The quadratic score turns out to be the complementary, having to do with the extropy as the complementary dual of entropy. This is the entropy-based score. This is the extropy-based score. You have to think about both of them, blah, blah, blah. And that's my story, and I'm sticking to it.
Thank you very much, Frank.
And thanks for being patient, because this is an extra special primary. It ran over 35 minutes, so Douglas is cut off.
Oh, thank you very much.
But we really enjoyed it, and I'm going to go back and watch the video. I'll probably post it on Vimeo, as well as YouTube, also from my webpage maybe. So if you have any questions for Frank, any burning ones, you can shoot them now. Otherwise,
the best way to answer your question is to, there are two copies of my book in the library, and you can also get it on Amazon as a downloadable thing. I'm not sure how much you have to pay for it. But,
I have a hard copy on my shelf as well.
Yeah.
If you want to borrow my hard copy.
It's on some, I wouldn't say it's on a lot of people's shelves, but it's on some people's shelves. That's what we can say about my book.
Oh, I know it's on my shelf.
I know it's on your shelf, too.
Well, that was the copy you gave Margaret, right? And I think you gave the copy to me at the end of the celebration of John Dealy's conference, which happened 3 days after I came here.
You can remember that?
Oh, remember I puked on the red wine? Yeah, I know.
I was going to say, you can remember that. You can remember that night?
Of course, yeah.
So,
all right, thanks very much.
Anybody like a beer? I'll buy beers if you have a beer before you go.
I'll take a beer from you.